concept we're going to talk about in this chapter about chemical bonding is the idea of bond length and bond energy, and specifically how we can use it to calculate the enthalpy of a reaction. So the first thing is, we've been talking about single, double, and triple bonds in drawing Lewis structures. When we talk about the strength of a bond, we usually use this term called bond order, where a single bond has a bond order of 1, a double bond order of 2, and triple bond order of 3. The way you imagine bond order is just the amount of glue that binds atoms together in covalent bonds. So the higher the bond order, the more electrons are present, which means the two nuclei are closer together. So bond length is the actual distance between the nuclei of the two atoms. So if you have a high bond order, then your bond length should be pretty short. In other words, a triple bond would have a shorter bond length than a single bond. Bond energy is the amount of energy you need to put in to break the bond. And so the higher the bond order, because the stronger the attraction would be between the nuclei and the electron, it will be a lot harder to break that bond. So a triple bond should have a higher bond energy compared to a single bond. And so you can see both of these in tables of bond length and bond energy. So here's a table of bond length. So just to compare the length of a single, double, and triple carbon-carbon bond, you can see that they progressively get shorter and shorter as we expect. Same thing here with the nitrogen-nitrogen bond. If we go to the table of bond energy, which is often called bond enthalpy as well, we see here that to break a carbon-carbon single bond takes less energy compared to breaking a carbon-carbon double bond. And then it's even harder to break a carbon-carbon triple bond. Now, the energy it takes to break the carbon-carbon double bond is not exactly double of that number. And for a triple bond, it's not exactly triple of the single bond. And we will discuss this a little bit more in the future when we talk about the type of overlap of orbitals that make up a single, a double, and a triple bond, because it turns out that it's not exactly the same, and that's what gives rise to the different levels of energy when you get this double and the triple bond. Bond energy is actually really useful in thermochemistry, because as long as you have reactions that are gas phase reactions, you can actually use these bond enthalpy values to help you calculate the enthalpy of that reaction. If you imagine a reaction, you take the reactants and you break them into the atoms, and then once you get the atoms, you recombine them to form the products. If you recall, this is kind of similar to the idea that we had when we used enthalpy of formation. We would take the reactant, we break them into their elements, and then afterwards we reform the elements in the same way as we have our products. It's slightly different here because in this case, we always break them into the individual atoms. With the enthalpy of formation, sometimes our elements are not atoms. Sometimes they might be diatomic species, right? Cl2, for example. Sometimes they might be atoms, but the atoms are not in the gas phase. Sometimes they might be carbon solid, sometimes they might be aluminum solid, etc. Okay, so there's going to be a slight difference there. The way we can calculate things is if we imagine we take a reactant and we break it into atoms, well, that energy that it takes to take your gaseous reactant and convert them to gaseous atom is exactly your bond enthalpy, right? So that part of the process then is just adding up all the bond enthalpy values of the various reactants you have, multiplied by the number of moles of each of the reactant. When you take the second step of taking all the atoms and combining them to form products, that step is exactly the opposite of the bond enthalpy step. Bond enthalpy is taking something and breaking it apart. If you're reforming it, then it's the negative values of the bond enthalpy. So if you recall in thermochemistry, if we have a process giving us a positive enthalpy value, if we reverse that process, then our enthalpy will become negative. So the way we can calculate the enthalpy of a reaction then, if we imagine this pathway occurring, is to take the bond enthalpy associated with all the reactants, which is in the breaking of bonds, plus the bond enthalpy associated with the forming of bond, which is just the negative of the bond enthalpy of the product. So your equation becomes delta H of the reaction is just equal to the sum of the bond energy of your reactants minus the sum of the bond energy of the product. Keep in mind, this equation is a little different than the one when we use the enthalpy of formation. In enthalpy of formation, we take the enthalpy of formation of products minus the enthalpy of formation of reactants. And the reason it's exactly opposite of each other is the way we define formation reaction and the way we define bond enthalpy reaction. In formation reaction, we're taking elements and we're forming a compound. That's why it's called a formation reaction. In bond enthalpy reaction, we're taking a compound and we're breaking it into its atoms. So it's exactly the opposite process. The formula that you derive using these two thermodynamic quantities are also exactly opposite from each other. So let's see if we can calculate the delta H of a combustion reaction using our bond enthalpy values. We're asked to calculate the combustion of propane C3H8, and recalling your knowledge of combustion reaction, you know that that's a reaction with oxygen generating CO2 and H2O if it's a hydrocarbon. So that should be the balance equation. And then the way we're going to do this is first we have to draw Lewis structures of all the species. And that's what I did here. I put the coefficients there to indicate how many of each of the species I have. The next step is I need to look up the bond energy of each of the bonds I have in here, tallying up of all the different bonds. If I look at the bonds, I have carbon-carbon, I have carbon-hydrogen, I have oxygen-oxygen, double bond, carbon-oxygen, double bond in CO2, and OH bond in water. And I have to count them. So just to illustrate how I count them, for the CC bond, for example, this carbon-carbon single bond, it's 1 and 2. For the carbon-hydrogen bond, it's 1, 2, 3, 4, 5, 6, 7, 8. And so that's where those numbers come about, the 2, the 8, etc. And you can repeat this for all the other ones as well. Once we do that, we're going to need values of bond enthalpy. So it's either given to you or you need to look up the values in a table. So I'm just taking the table that I had from the lecture notes and bringing it here so you can see the values of the bond enthalpy. And what I've done here is put it in that table for each of the values of the bond enthalpy. And then the numbers here represent the actual total energy when I multiply 347 times 2. So I got those numbers. Those are all my reactants value. And then I got these two numbers. Those are my products value. One thing I want to point out is CO2 is unique here because there is C double bond O in molecules like aldehydes, carboxylic acid, and so on. And the strength of those C double bond O bonds would be 736, but then for CO2 it's actually 799. So it's more stable in CO2. So you want to make sure you use the correct value for bond energy there. And once you get the value for reactants and products, all you need to do is apply that formula of delta H, which is the sum of the bond enthalpy of the reactants minus the sum of the bond enthalpy of the products. And subtracting those two values, the 6496 comes from adding all these numbers together. The 8506 comes from adding these two numbers together. You're going to get negative 2010 kilojoules for this combustion reaction. And that makes sense. You know, you expect a combustion reaction to be exothermic, right? So you do generate a lot of energy from combusting propane.